Today I'm going over a generic-based board game project that I recently created using C++. My project allows users to play either Tic-Tac-Toe or Othello. I also created a graphical user interface so that the user can actually click and interact with the game board. Let me briefly go over the different parts of my project before I show you the demo. So I use a Model View Controller or MVC Design Pattern to divide both the Tic-Tac-Toe and the Othello games into their respective subparts. Both games have classes that define the game board and also what constitutes a game move. This is the model. Each also has a class that displays the game board to the user, which is the view. And finally, the generic based games file responds to user interactions, controls the overall game flow, and it prompts the game views to update accordingly, which is the controller. I mentioned before that this project utilizes generics, so let me cover that aspect as well. If you look here, you may have noticed that I have generic files for a game board, a game exception, a game move, and also a game view. If we take a look at the different Othello board and Tic-Tac-Toe files, we can clearly see that they inherit these base game classes. These both inherit game board, these both inherit game move, and these both inherit game view. You may be wondering how this affects the project, so let's jump over to the generic based games file to find out. The pointer variables that are used throughout the project are of type game board, game view, and game move, which are the base classes. This is where the beauty of generics kicks in. When the user selects a game mode, I simply initialize the variables to the appropriate game type, and that's it. I don't need to constantly check which game mode's being played before I do anything. I just plug in the generic variables and I let the derived classes do all of the work. This makes the overall game flow intuitive and easier to understand in my opinion. Let's move on to the demo. Going to start a fresh instance of the program. To start out, the user is given the option to select the game mode. They can either click on Tic-Tac-Toe or Othello. I'm going to select Tic-Tac-Toe first. An empty Tic-Tac-Toe board is displayed to the user and the current player's turn is displayed under the game board. I can click anywhere on the screen and nothing happens until I click on an empty space inside of the game board. This makes that empty space on the game board mine and changes it to player 2's turn. Nothing happens if I click on the square that was just claimed by player 1. I need to click on a different empty square on the game board to progress. The game continues until somebody wins or there is a draw. When someone wins, I highlight the winning line and I display the winner at the bottom. Now's a good time to go over the menu options. The File menu has the option to select the game mode, to start a new game, and to exit the program. These options also have their own keyboard shortcuts, which are also displayed. The Edit menu gives the user the option to undo the last move or pass their turn. And finally, the Help menu just provides a very simple About section for the program. I'm going to start a new Tic-Tac-Toe game using the keyboard shortcut, which is Control-N. When I do this, a confirmation pop-up appears. Selecting yes will give you a fresh game to play, and selecting no will cancel the new game command. The next thing I should do is show you what a draw looks like. I'm going to fill in the board game, trying not to win along the way. The winning message at the bottom now informs the user that the game was a draw, and the occupied cells are also shaded in a purple color, which is the combination of player 1's blue color and player 2's red color. Let me go to the game mode selection now so that I can show you the Othello game. So here's the Othello game in all of its glory. Going to move the window around a bit and make it a little bit bigger. For anyone who hasn't played the game of Othello before, the objective is to have more pieces in the end than your opponent. The game only progresses when the player clicks on a valid square and captures an opponent's piece or pieces. I make sure to shade all of the valid moves in with gray so that you know all of the available moves. The score is updated every time that a move is made. You can see this happening dynamically next to the player names. Now the game ends when either all of these squares on the board are occupied, when neither player can make a move, or when both players pass their turn consecutively. Right now I'm just adding some moves to the game. Keep in mind that I'm not really being strategic with my moves. I'm more so going for quantity over quality right now. Going to fast forward to a fully occupied board. I will see you guys in a bit. So here's a finished game. I display the winner at the bottom, and I also shade in all of the winning player's pieces with the appropriate color. I haven't demonstrated the undo feature yet, so let me do that for you. The keyboard shortcut for undoing a move is Ctrl-Z. I'm going to use this shortcut a couple times so that you can see the moves being undone. Now let me end the game by passing twice. If you recall, the keyboard shortcut for passing a turn is Ctrl-P. If I use Ctrl-P twice, the game's now over. This time player 2 won, and I made sure to shade all of their winning pieces in red instead of blue. I think that's a pretty good stopping point for this demo. There is one really cool aspect about my project that I wanted to talk about before I do go though. So typically with a project like this, you would use a two-dimensional array to store the game board values. They're extremely convenient at holding values for grid-based games because their structure in itself is also very grid-like. This makes accessing values super straightforward and easy. Well, I actually didn't use a two-dimensional array for storing the values. I just used a one-dimensional array instead. This seems like a really simple change at first, but once you start thinking about it, this change actually impacts the board game tremendously. When a location is selected in the array, there's no conventional way to determine the location of all the adjacent pieces in a one-dimensional array. As you can imagine, this made verifying the validity of the user move a lot more complicated, especially when it came to Othello. In Othello, we have a game board that is represented by 64 individual pieces, and in order to make sure that the user clicked on a valid square on the game board, we need to first make sure that the square is empty, that there is at least one enemy piece next to that square, which is achieved by checking the 8 adjacent directions, and that there's at least one of your own pieces after the enemy piece or pieces. That's no small task if you're only given a one-dimensional array. There are a lot of steps that need to be taken to ensure that you're still going in the same direction and that these rules of Othello are still being satisfied. Let me show you how I ended up doing it. So as this new game shows, there are a couple of possible moves that I can make. For this example, I'm focusing on this move right here, which is index 26. Here is a visual representation of the Othello board array, which has 64 elements to it. Make it a little bit bigger. It goes from 0 all the way to 63. On this game board, we can see that index 26 is a valid move, but how do I know this? When figuring out the solution, I found it a lot more useful to use this diagram. Keep in mind that the Othello board array is still structured as a one-dimensional array, so it goes from 0 all the way to 63. But for the sake of visualizing what's happening, I found it easier to use this image right here, which shows the index values in groups of 8. This diagram made it a lot easier to determine the correct offset that needs to be added to the index to travel in a particular direction. To go northwest, we would subtract 9 from the index. 1, 2, 3, 4, 5, 6, 7, 8, and 9. To go north, you'd subtract 8. To go northeast, you would subtract 7. To go east, you'd just add 1. To go southeast, you would add 9. To go south, you would add 8. To go southwest, you would add 7. And finally, to go west, you would subtract 1. That's exactly what the getDirectionalOffset function does in the Othello board class. It returns the exact offset value needed to travel in a particular direction. That's actually half of the solution, believe it or not. The other half revolves around determining whether traveling in a specific direction is still inbounds or not. This is tricky because just being inbounds of the Othello array isn't actually enough. It also needs to satisfy the rules of Othello as well. Now, computers excel at determining patterns, so naturally I went looking for a pattern. Lo and behold, I found one when you perform a modulus of 8 on the index values. It turns out that the index modulus 8 gives a value ranging from 0 to 7. And these results actually repeat themselves all throughout the array, which totally makes sense. Let me pull up another diagram to help you visualize this. The indexes I put in the upper left-hand corner, and their modulus values, when you perform a modulus 8 on them, are all centered in each cell. As I previously stated, this pattern of 0 through 7 repeats itself all throughout the array. So how is this helpful? Just to reiterate, we are using index 26 as an example. So I actually have one final diagram to show you guys so that we can put this whole picture together. Index 26 is grayed out so that we know which move we are working around. I also shaded in each direction with its own appropriate color and created a key for them as well. Now the question becomes, how do we determine whether traveling in a desired direction is still inbounds or not? This is where all of these different modulus values come into play. When traveling northwest, south, and southwest, we can see that all of the modulus values are decreasing by 1. As long as we stay in bounds of the original array, which is between 0 and 63, and the modulus values are decreasing by 1, then we are still in bounds while moving in those 3 directions. When traveling north and south, we see that the modulus values stay the same. And finally, when traveling northeast, east, and southeast, the modulus values are actually increasing by 1. An example of this pattern being broken would be at index 24 and moving west. The offset value that we need to add to the index to travel west is -1. So we would subtract 1 from index 24, and we end up being at index 23. This index is in bounds of the original array, but the modulus value is now 7, which doesn't follow the pattern of being 1 less than the previous index. This means that we are no longer in bounds while traveling west. This idea holds true for all of the other directions as well. As long as they all follow the same pattern and are in bounds of the original game board, then traveling a space in that direction is still considered in bounds. As soon as that pattern's broken, or the new location is no longer in bounds of the original array, then traveling in the specified location is no longer in bounds. And these exact ideas are reflected in the directional inbounds function. We make sure that both the previous index and the new index are in bounds, and we also make sure that they are following the appropriate pattern based on what direction they're traveling in. Now that we have a way to determine the offset and whether traveling in a direction is still inbounds, everything else just becomes business as usual. In the apply move function, we first check all 8 surrounding directions to see if there is an enemy piece located next to the selected spot on the board. After we find an enemy piece, then we keep traveling in the same direction, making sure that everything is still inbounds along the way. And once we find our own piece, we then start backtracking and claiming all of those enemy pieces as our own. We also update the board values accordingly. When we get back to the original spot, and we add a flip set to the move so that we know what direction and how many enemy pieces were captured. And then we add that move to the back of the history vector. Also update any board values one last time to reflect claiming that empty spot as our own now. It did take me a while to figure out the correct pattern to use, but once I did, it was extremely satisfying seeing everything come together. There are so many cool features that I haven't discussed yet, like the center dialog boxes, which aren't a native feature, surprisingly. The resizing differences between the game types, showing the user all of the possible moves, etc., etc. I think I've rambled on enough for today though, so we'll leave it at that. If you are interested, there are plenty of comments in the code to help you navigate through the different aspects of the project. As always, feel free to contact me if you have any questions, and I'll be happy to help. Thank you for tuning in, and enjoy the rest of your day.